I'm Victoria from IBM Research Zurich, and I'll be presenting this work developed at George Mason University on Retina-Inspired object motion segmentation for event cameras. We take inspiration from the inherent problem in DVS cameras or event cameras of ego motion. DVS cameras are bio-inspired visual systems that capture per pixel brightness changes in an asynchronous way. However, when the cameras are mounted in a moving platform with microsecond temporal resolution, high dynamic range, which are very applicable to robotic applications, if the camera is mounted on a moving platform, then all of the spikes correspond to effectively the changes in the scene, whereas, for example, moving objects. However, if the camera is mounted on a non-fixed position, such as a drone or a robot, then a lot of spikes are generated from the background movement, which are called ego motion, and therefore tracking moving objects becomes very difficult. How can we suppress this ego motion to identify independent moving objects from DVS cameras? And our response was to take inspiration from the mammalian visual system that inherently suppresses the eye's motion to catch prey and defense from menacings. This mechanism or feature is known as object motion sensitivity. In the retinal layers, initially the photoreceptors that contain sensitive pigments and they translate the photons into electrical currents. Then the bipolar cells adapt rapidly to luminance changes and they depolarize or polarize in the presence of light. This mechanism is already followed or imitated by dynamic vision sensors. However, a more refined version of the information is performed at the intricate layers of the retina, specifically in the ganglion cells. The amacrine cells perform some sort of lateral innervation between interconnected bipolar and ganglion cells. And then the ganglion cells refine this visual stimuli into spike trains to send visual-rich information through the optical nerve. So taking inspiration from the neuroscience, interconnected bipolar cells and ganglion cells respond to designated areas of the visual stimuli, which are known as visual receptive fields. These are more well known in the computer vision field as variable size circular sensory units that have a very important role in perception. There are two designated regions in the visual receptive fields that we take into account, which are the surround and center regions. A center receptive field is defined by a direct connection between bipolar and ganglion cells, whereas the surround region of the receptive field is defined by an indirect or inhibitory connection between bipolar and ganglion cells through amacrine cells. Both these regions have been defined by experimental neuroscience to be the ones responsible for suppressing the animal's motion when both the animal and the environment is moving. The global motion that includes eyes motion and environment motion follows a different pattern through the center receptive field, whereas a local motion is defined at the surround receptive field. The amacrine cells contrast signals from a global area, including eyes motion and environment motion, and subtract them from a local motion area, resulting in some sort of response to differential motion. We take inspiration from this simplified biological circuit, and we model the surround and center receptive fields as convolutional kernels. They are well defined in computer vision as imitating the receptive fields. Additionally, since dynamic vision sensors already take inspiration from bipolar cell behavior, we take them as the input of our convolutional kernels, and therefore we only perform the second retinal synapse, which corresponds to amacrine and ganglion cells. Additionally, we model them as Gaussian kernels, since these circular size sensory units in the retina more or less focus in the middle of the visual stimuli, thus carrying more significance due to the focus. We perform the convolution of an input DVS image or frame, performing a concentric convolution at all times, whereas the surround always carries twice the size of the center filter, and performing a concentric convolution independently. We finalized with two feature maps as two convolutional kernels. One of them would correspond to the global motion, and the second one, the center feature map, will correspond to the local motion. By performing, let's say, an inhibition between these two feature maps, and then trying to perform some sort of spiking neuron activity of the ganglion cells, we effectively more or less try to replicate the spiking activity at the ganglion cells to respond to object motion sensitivity. Additionally, since we went for a very low overhead simplified algorithm, instead of dealing with the full point cloud of event streams, we accumulate over a small time window of 5 milliseconds in order to have a 2D version of the DVS frames. And in order to judge the performance of our algorithm, we selected a set of data sets that account for a set of point clouds for event streams where the camera is moving as well as moving objects. And in addition to that, some sort of ground truth label to compare the performance. In this case, we selected data sets that provided a per pixel motion segmentation task, where pixels activated correspond to independent moving objects and 0 correspond to background. We selected 2 data sets from the state-of-the-art, EVIMO, which is a real event dataset captured with Davis 346 camera at 200 Hz, where the camera has different types of trajectories, and in addition to that, up to 3 moving objects in the scene, as it is shown in this video. There's an additional motion mask capture system functioning at 40 Hz in order to generate the segmentation masks. And in addition to that, we also use the moving object dataset, which is a simulated 3D environment with up to 8 moving objects and different camera trajectories that is then passed through a DVS simulator. And in order to judge the performance, we use the common known metrics from the state-of-the-art, which are the intersector of a union that measures the overlap between the predicted mask and the one from the ground truth, as well as the detection rate that considers that an independent moving object has to be correctly detected if the mask overlaps in more than 50%. We did some benchmark comparisons with many state-of-the-art methods, and we evaluated that along all of the sequences from EVIMO validation dataset. The first row corresponds to some background objects that are in a static position. So for example, box would mean there is a moving object moving in front of a static box, which might complicate or generate or increase the amount of spikes. We evaluate that against these many state-of-the-art methods, we reach very comparable accuracy, despite having a learning-free method, making it more domain agnostic and applicable to different scenarios. In addition to that, we also compare the mean integer over union all over the entire validation data set of these 2 data sets. And as well, we land very promising results. And most importantly, if we compare with all of these methods that, first of all, are based on learning pipelines or parametric estimation of the camera movement by taking also additional data from the camera or the robot, we only account for 80 non-learnable parameters, which represents from 3 to 6 orders of magnitude in parameter reduction, making it more suitable for robotics, edge applications, and low latency. And here's more of a visual representation on how the OMS algorithm would work. We can see that in many of the frames, we more or less capture effectively only the moving object. For example, a plane, a mug, and a plane again. However, the main shape or structure of the objects is still a bit deteriorated compared to, for example, learning methods. However, in order to recognize effectively the coordinates of the moving object, we landed very good performances. Our method achieved top performance or very comparable performance to state-of-the-art methods with between 3 to 6 orders of magnitude in parameter reduction. It's learning-free, bio-inspired, which makes it more domain agnostic and applicable to the actual application scene, which are low power solutions. And we also would like to keep taking inspiration from all of these refined versions of the retinal ganglion cells in order to incorporate additional visual features to more intelligent visual systems. This work was done also in collaboration with Northwestern University and University of Wisconsin. And I would like to thank also National Science Foundation for the funding through this project. Thank you very much.